Welcome to ES Repair. I'm your host, Mr. Fix-It. Today I'm going to show you different types of power inverters. Everybody these days are probably using a power inverter of one kind or another. Use everything for laptops on the road. All you have to do is hook them up to a 12 volt source. You instantly have 120 volts AC to power anything from light bulbs, laptops, chargers, phone chargers, anything that requires 120 volts in an RV or truck. You can use a power inverter. I'm going to show you what to do and how to hook one up and show you the insides of these inverters and what makes them function. Here I have sitting here is a very old, one of the first ones that came out. Whiz Kid found this in a junkyard somewhere. And this is one of the old first 1000 watt power inverters that ran off of 12 volts DC. As you can see, they are pretty bulky. They're huge and they're heavy. And this in here would only put out 1000 watts. I got the cover and stuff off to show you the insides of the different parts of a component. This one here used an old gigantic transformer, which is mostly the weight in this whole thing. Back here you have a controller which provides the oscillation that is required to get the transformer to jump 12 volts up to 120 volts in order to use it. You can see how these wires are all thick, bundled up. You got your switch, controller, transformer. In front you have your connections to hook up to your battery. You have your breaker switch, control overloads. You got your outlets. You got a remote control switch, so if you're in the front of the cab or front of the vehicle you can remotely turn it on. And you have an indicator to let you know it's turned on, and a power switch to where you can turn it on and off. Over the years, as technology got better, now they're beginning to get smaller and more compact. The technologies has improved quite a bit over the years. This one, as you can see, I'm taking apart and show you the difference between the old versions and the new versions. As you can see, there's a huge difference. In this one, you have your 12 volt input. It has also a little fan in it to help keep it cool while it's running under a load. You got your front with your outlets, your vents for the breathe, a power on switch, an LED to let you know the power is on, and if there happens to be a fault, a red light will come on and buzz. Inside, you have your transformer that jumps to power from 12 volts DC to 120 volts AC. Now these things do not put out a sine wave like your normal household current will. They put out what's called a modified square wave. The difference is this one here is a newer technology. This one here only used what was called square wave. And here I'll give you a demonstration of what I'm referring to. Here you see three different types of waveforms currently used in today's power inverters. The first one you see is the sine wave. The sine wave is has a smooth arch when it goes positive, and then has another smooth arch when it goes negative. This waveform represents 1 cycle or 1 hertz. Next we're going to see square waves. As you can see the difference, the square wave, which is identified in blue, goes straight positive for a half the cycle and then goes straight negative for the other half of the cycle. The problem with this is that most equipment and devices could not function with this waveform without causing some type of damage, or they would malfunction. The sine wave is used in higher priced power inverters, but of course you will pay a hefty price for those types of inverters because they have extra circuitry inside them to produce a true sine wave output. The only sine waves that you mostly see are in homes. Next, we're going to see a modified square wave, or some places call them something like approximated stepped wave. As you can see, it's marked in the orange. The orange looks kind of like a square wave, but its peak is much more closer to what a true sine wave goes, as you can see here. But as it falls back when it finishes its first cycle, you can see there's a pause between the time it finishes the cycle to the time that it goes negative. This is a compromise between a sine wave and a square wave. This allowed more equipment and devices to function on a square wave, which is modified to simulate as close as possible to a full sine wave currently used in homes. It is more cost effective than a true sine wave, and yet it's more affordable. But yet some devices do have to have a true sine wave. I yet have to find one. Most inverters that I've ever used, and a lot of them I still have, use this type of waveform. What you can do, that's what these fans are for. Now I can show you what to look for in a power inverter. In the front, it will say DC to AC inverter. Above it, nearby, it will say 400 watts. This is the amount of power this inverter can provide continuously. Most of them do have what's called a peak, which is pretty short. That's only starting like electric motors. Well, in order to do this, most of these will come supplied with their own cables that you can hook up. This one, for instance, came with a 12 volt adapter where you can just plug it to a 12 volt lighter. It also comes with an adapter so you can just hook it up to a pair of batteries on your pickup truck or your RV or tractor trailer. The way you hook these things up, if you're going to use your cigarette lighter, you need to undo the back parts. Most of these have it just screws right off. Put your red, matches your red to your positive. Most of them are marked. It must be positive, and it will connect to your positive battery if you use the battery cables. The ground, which is the black one, will hook up to the black posts. And these are color coded on the back side of the inverters. You want to make sure that they're tied down nice and tight. They're not wiggly or loose. Next up, all you have to do is just plug her in to any 12 volt power source. Then you can turn it on and you can see the light comes on. Sometimes I'll have a red light to come on because it goes through a check to make sure everything's functioning, and then it goes out. Then you can plug anything up to 400 watts. I'm going to use my tester to see the voltage that's coming out. Set it for AC. And as you can see, currently it's putting out about 114 volts, which is normal. Most ACs, they run between 115 to 125. Right now it's under a no load. Once I put something under a load to it, the voltage will change, but not much, usually within 1 to 2%. They're very simple to use. They're nice and compact. You can get inverters as large as 3,000 watts, which I have no reason for why somebody would want something that big, but most of the ones I've used is 1,500 watts. That does pretty much what I want it to do in my truck. If you want to use a higher wattage, such as 1,500 watts, or this one here, which is 1,000, wire size is going to make a real big difference. This one here has got the lugs on the front of it. For things like if you're going to run, say 1,500 watts, if you want to run, it's going to run about 125 amps. Well, the wire size needs to match. The wire size has to be matching. You can use anywhere between 4 gauge to 0 gauge on this inverter. The bigger the gauge, the more capacity. The problem is if you use too small of a wire gauge, the wire tends to heat up because of the high current demand. And if it gets too hot, it can melt the plastic insulation that's around the wires or the cables that you're using and can cause a fire. If the heat gets too extreme, this melts, and then if this metal contacts to a ground, it will short something out and possibly catch fire. So if you want to hook something up this big, you want to make sure that you use the right size cable. You can go to different stores. Most of these high-powered inverters will come with their own set of cables. The shorter you can run them to the battery, the better they will perform. The bigger the wire gauge you use on them, the better they will perform. Now, I will show you a calculation that you can provide to determine how many amperage and what size wire you will need to run something this large. This is a demonstration to show, because when you buy an inverter, the inverter does not tell you how much current it will require to put out its rating. For instance, a 1,500 watt inverter does not tell you how much power it's going to require to produce 1,500 watts. So here I'm going to show you how you can calculate all that. And then I'm going to show you recommendations or a table to show you the distance of a wire depending on the size of the wire and how much current that wire will be pulling per foot. This demonstration will show you how to calculate your current capacity required for the inverter. This, for example, this is going to be 13.8 volts, which is identified by VN. The output is going to be providing by 120 volts AC, identified by Vout. The maximum rating is 1,500 watts. At 1,500 watts, you can divide 1,500 watts by 120 and you will get 12.5 amps. The next formula will show you the reason why you have to know the wattage. Most inverters nowadays are 87% efficiency, which means the power conversion between DC to AC is only 87% that is transferred. The rest of it is lost in mostly heat, especially when you're at the maximum capacity. So what is the input amperage required at 13.8 volts DC, providing 120 volts AC at 12.5 amps of 1,500 watts? This is the formula. Current in will be our variable. This is what we want. This is what we're wanting to find out. V out, as we know, is 120 volts AC. The current out, as we know, is 12.5 amps. Well, when you multiply voltage times current, you get the wattage, 1500 watts. Well, since the inverter already told us it's a 1500 watt inverter, this isn't always necessary. Because what you have, this number here is the total wattage that the inverter is going to be providing. So you take your V out, which is 120, multiply it by the current out, which gives you the total wattage. Then you're going to divide it by whatever V in, which is 13.8 volts, times the efficiency, which is 87%. So let's fill in the blanks. As you can see, all the numbers are filled into the proper places. 0.87 is equivalent to 87%. That is a decimal form. Now, let's solve the problem. As you see here, 120 times 12.5 is 1500 watts. 13.8 times 0.87, or 87%, equals 12.006. The next step will be to divide 1500 by 12.006, and the answer is 125 amperes, or amperage. This is what the inverter will require at 13.8 volts, 125 amps, to provide 12.5 amps of 120 volts, providing 1500 watts. That's a lot of current, a lot of power. And I'm going to show you next on how difference a voltage can make. In the next demo, we're going to substitute 12 volts. It's only 1.8 volt difference between 12 and 13.8. We know that 13.8 requires, the inverter would require 125 amps. So let's substitute 12 volts for the same output ratings. Substitute the variables, and you come up with 144 amps. As you have noticed, 1.8 volts increased the current the inverter's power requirement up to 144 amperes. So, what happens if we use 14.1, which is mostly provided when the vehicle is running, because the alternator provides 14.1 volts. Now, the current capacity of the alternator does vary by vehicle and make. So let's substitute the 12 for 14.1 and see what the difference would be. That is a pretty big difference. For 14.1 volts providing the same amount of power output of 1500 watts at 120 volts AC, it only requires 123 amperes, which is a lot better than providing a 144. Big difference. So, to summarize it, we've noticed that on a 12 volt supply, the amperage was at 144 amps. to provide 120 volts at 12.5 amps of 1500 watts total. Now if you were to take your voltage, multiply it by the amperage, you would get your wattage or power. For a 12 volt system, 12 volts times 144 provides 1728 watts. Have you noticed something? The inverter is only putting out 1500 watts, but it's taking more to produce it. Almost 200 more just to produce 1500 watts. Next, okay, let's check 13.8. Well, at 13.8, it only required 125 amps. But it's requiring 1725 watts. Just to do 120 volts AC, 12.5 amps at 1500 watts total. It's still using more. Next, we have 14.1. Even though the amperage has dropped to 123, it's using more wattage. 1,734 to provide the same amount of power output. This is where the 87% efficiency comes in, because the remainder of the 13% is wasted in heat. Now, when installing your power inverter, you can use this table as a rule of thumb. It's not exact science, but it gives you an idea of what to expect. For instance, if the cable you have to run, which is the positive one, and that's the red cable, if it runs from the battery to the inverter, up here would be the feet. You got 1 to 4 feet, 4 to 7 feet, 7 to 10 feet, and so on and so on. Here you have the amperage, 1 through 20 amps, 20 to 35 amps, 35 to 50 amps, all the way up to 125 to 150 amps. Now, to get an idea of what size cable you should use, I'll show you an example. Let's say from your battery to your inverter is 7 feet, or you can say 7 to 10 feet. Well, here's 7 to 10 feet. Here's a column. We calculated 12 volts to be 144 amps. So we look down here. This says 125 to 150. We would have to use 2 gauge cable between 7 and 10 feet. Now, if you were to use 14.1 volts, which means your vehicle's probably running, we noticed that it was only required to run 123 volts. Well, for 123 volts at 7 to 10 feet, we look right here, 125 to 125. We go over here to under 7 to 10 feet, and what do we find? 4 gauge. 4 gauge cable is what you can use to run at that rating. So, as a reminder, to use your cable, you want to get a real good idea of how far that cable will have to run. The only cable that needs to run to the battery is the red cable, which is also your positive cable. The black cable can be tied to the chassis. As closest to the chassis as you can run it will be preferred. So the only cable that you will have to run is the positive. The better the ground, the better your power inverter will work. Now, when you're installing the power inverter, some of them also have what's called a physical ground. The physical ground needs to be tied into the chassis as well. This is in case that your device or equipment that you're using happens to short out. All inverters do have fuses inside of them, but that's to only protect the components inside to prevent it from catching fire if something was to go wrong. When installing power inverters, it's a good idea to install a fuse between the battery and the inverter. So in the event that a wire is cut into or pinched or shorts out somewhere down the line, it doesn't start a fire. The best way to rate a fuse is most of them, you calculate your wattage. You use this formula I showed earlier in the broadcast to determine what kind of amperage you're going to be required, and find yourself a fuse that is larger, slightly larger than what you're needing. That way you protect your vehicle, because if a short takes place, it can do some serious damage and possibly cause your battery to explode. Another note, when installing power inverters, you want to make sure that your alternator can handle the power requirements of your inverter. For instance, if your inverter will be using or requiring 123 amps, as I demonstrated earlier, you'll want to get a fuse about 130 to 135 amps. You're not going to find them in any local store. Most of those fuses you have to specially order. But it is always good to have them hooked up in case of a fault. The alternator will have a label on the side of it, tagged on it, telling you the voltage it puts out and its current rating. Some of them range from 60 to 200. When you calculate your inverter's requirement, check the alternator and see if it can handle that power inverter. If not, you'll either have to make your alternator get bigger to have more current capacity, or you're going to have to go for a smaller inverter.